If you ask for directions and someone says, just drive 20 miles, you might end up lost. But if they say, drive 20 miles due north, you know exactly where to go. That difference is the dividing line between two types of physical quantities. A scalar quantity is fully described by just a magnitude, a number. We don't ask, in what direction does the truck weigh 10 tons? On the right, a car's velocity is a vector. Knowing it's moving at 50 kilometers per hour is only half the picture. We need to know it's headed east. To map these vectors mathematically, we represent them as arrows. The length of the arrow gives us the magnitude, and where it points gives us the exact direction. Working with only magnitude leaves gaps in our physical model. Including direction allows us to calculate precisely where an object will end up. Because vectors include direction, adding them isn't as simple as basic arithmetic. If you push a box with a force of 3 newtons, and a friend pushes with 4 newtons, the combined force is only 7 newtons if you both push in the exact same parallel direction. Using the head-to-tail method for different angles, connect vector B's tail to vector A's tip to draw the resultant vector. To subtract vector B, simply flip its direction 180 degrees, attaching it head to tail to find the completely new resultant. To track these directions numerically, we use an XY coordinate plane anchored by unit vectors. These unit vectors, often labeled I and J, have a magnitude of exactly 1. Their only job is to align our calculations with the horizontal and vertical axes. Figure 2.1 shows a diagonal vector A forming a right-angled triangle's hypotenuse. Its horizontal projection, OM, acts as the x component, and the vertical projection, ON, acts as the y component. The adjacent x component uses cosine, giving equation 2.2. The vertical y component uses sine, giving equation 2.3. Pause the video and calculate the x and y components for a 10 Newton force at a 30-degree angle. For the horizontal, 10 times cosine 30 is 8.66 newtons. For the vertical, 10 times sine 30 is exactly 5 newtons. By applying these ratios, we take a complex diagonal force and split it into clean, independent horizontal and vertical numbers that are easy to work with. We can now handle multiple forces simultaneously using a 4-step process called the component method. First, sum all the x components. Second, sum all the y components. Third, use the Pythagorean theorem to find the final magnitude. And fourth, use the inverse tangent to find the final direction. Let's apply this to a typical exam problem. If an object is pulled with a force of 5 newtons east and 5 newtons north, we list the sums. Our x sum is 5. Our y sum is 5. We square them both, add them to get 50, and take the square root. The resultant magnitude is 7.07 newtons. To find the angle, we take the inverse tangent of the y sum divided by the x sum. Inverse tangent of 5 divided by 5 gives us 45 degrees. Because both forces are positive, we can visually confirm this vector sits securely in the first quadrant, so 45 degrees is our true angle. Before taking the DPE 803 exam, keep these rules on your cheat sheet. Remember that unit vectors strictly have a magnitude of 1. Also, if a problem asks you to subtract a vector, you must reverse its direction before calculating. Moving past basic arithmetic and applying trig functions allows us to break down any force on a coordinate plane. Mastering vector resolution gives you the exact mathematical tools required to predict motion and ace the basic science paper.